Okay. So remember what we're doing. We are trying to basically use the residue theorem to evaluate improper integrals, right? So the trick is to you have some. You're asked to evaluate some real integral, right? And what you do is you see you by some way or another, from knowledge of calculus, say you determine that this integral actually converges. Once you show that it converges, then you can evaluate it as a principal value integral, right? So you check first. You check that it converges. If it does, as long as it converges, then you see that you can evaluate it as a principal value integral, right? That's to say that you can evaluate it on this symmetric domain, right, as R goes to infinity, right? Okay, and then what you do is you say, well, let's take this thing, and instead of evaluating this thing by itself, let's construct a contour integral for which this is part of it, right? So you let gamma sub r be the usually the upper semicircle of radius r, right? Where this upper part of the upper part is called C sub r, right? And then you integrate fz dz over gamma r, right? And that's your original integral of interest, plus this integral over C sub r, right? And what's good about this thing is that if you're lucky, then you can evaluate this as using the residue theorem, right? So as r goes to infinity, this thing is going to eventually capture 2 pi I times the sum of all the residues in the upper half plane, right? So that's the trick, right? You take the limit as r goes to infinity of both sides. So you're hoping that two things happen, where you're hoping that, so what this is going to be is 2 pi I times the sum of the residues of f over Ci, the singularities in the upper half plane, right? And what you're hoping is that you have some conditions on f so that this integral vanishes, right? Or maybe you can evaluate it. But typically, what we're going for is that you're hoping that this integral goes to 0 as r goes to infinity, right? So this goes to 0, and once you have that, then the integral, that the principal value integral that you're hoping for turns out to be this thing, right? So that's the strategy. Okay, everyone awake? Okay. So last time we found some conditions on f for this to work out, right? So we ended last time with this theorem that said that if f is analytic on the closed upper half plane with finite number of singularities, z1 through zn in its interior, so not on the real axis. If there exist m, r naught, and p, where p is some real number bigger than 1, such that f, the size of f was less than or equal to z to the p, m over z to the p, outside of some disk in the upper half plane, right? As long as you had this sort of decay, right, then that would guarantee that this integral over C sub r vanished, right? Because you would end up with pi r over r to the p, where p was bigger than 1, and you'd end up with some small power, at least a small power of r on the bottom, and as r goes to infinity, then that thing vanishes. Right? So that was all that was enough to give it to you. Right? You needed p to be bigger than 1. Okay, so in that case, things worked out, and the integral indeed turned out to be what we said it was, the sum 2 pi I times the sum of the residues. Okay, so that's where we finished up last time. Okay. Now the question is, what about so now we're interested in a slightly different integral. What about integrals of the form f of x sine ax or f of x cosine ax? So let me put down a concrete example where a is not equal to 0. So for example, if you're asked to integrate cosine of 3x over x squared plus 1 quantity squared dx. Okay. Okay. So what do you think about this? Right? Can we just say, well, we can use the same thing that we had before? There's a little bit of a problem that may not be completely obvious, which is that so it looks like we might be able to do it, right? But the trouble is this, that if you look at when we look at this thing on the upper half plane, we're going to be taking the cosine of 3z, right? Where z is some complex number, right? Okay, so it's true that if x is some real number, then this is smaller than 1. Right? The magnitude of this is smaller than 1. But it's not true when you're taking the cosine of some complex number. So the size, if you look at say the size, if you look at the size of sine az, it actually turns out to be sine squared ax plus hyperbolic sine squared ay, where z is x plus iy. Okay, where the hyperbolic sine is e to the ay minus e to the negative ay over 2. Okay, so there's trouble because what that's telling you is that the size of the sine is basically like e to the ay, right? The size of the sine is like e to the ay. So if a is positive and we're heading up into the upper, we're heading upwards, then we're in trouble, right? Because e to the ay, is not something that we can bounce by some constant, right? That's what we would hope for. It's not possible, right? And similarly, for the cosine, you get this sort of thing. Okay, so you have exactly the same sort of trouble. Okay. So this what we tried before isn't going to work. Okay. So instead, what we do is, so instead we play trick number 3, I think. So trick number 3 is realize the integral as not part of a contour integral, but the real part or the imaginary part of some contour integral. The real or imaginary part. Right. The integral from negative r to r of f of x e to the I ax dx is, has a real part and an imaginary part, right? F of x cosine ax dx plus I f of x sine ax dx. Right. So this is the sort of thing. These are the sorts of things that we're interested in, and so you think, okay, well maybe we can evaluate something like this, right? So maybe we're interested in evaluating something like this, and if you think about it, the absolute value of e to the IAC is e to the negative ay. So maybe this gives you some hope that that this sort of thing could be evaluated, and of course it can.
Don't you still have to do the other trait function? Like if you're solving for the cosine one,
Yeah.
you still have to do the sine one as well as the one on the left.
No, we'll just take the real part of it. Right, we'll evaluate this thing, we'll take its real part when we get to that part. So. Right, so this is, you're trying to get one or the other of these things. So you evaluate this, you take this, you get this thing, and then take its real part, or its imaginary. So let me, so this actually, turns out to be pretty straightforward. Let's go back to the example. Cosine 3x over x squared plus 1 of the squared dx. Okay. So, so as before, let gamma sub r c sub r be as before. And we're interested in let f be e to the I3z over z squared plus 1 to the square. Okay. And what you see is that this thing has double roots, double poles, double poles at plus or minus half. Right, that's all right. Okay, so right, so okay, so right, so right, so we're trying to evaluate right. So what do we do? We calculate the residues as usual. Calculate the residues at positive I, and your phi is going to be e to the e to the I 3z over z plus I quantity squared, right? Z squared, yeah, z plus I quantity squared, right? And you work it out, you get that the residue at plus I turns out to be 1 over I cubed. Okay, and so what you get is that the integral of f over gamma r, as long as r is bigger than 1, is going to be 2 pi I times that. In other words, 2 pi over e cubed. Yeah.
So with this phi of z thing that you did, you just used where you characterize the pole as some phi of z over.
Yeah. So using the same notation, same notation as before. Right. This is the you want phi of z over z minus I squared to be your original function.
Mm-hmm.
Right. So that's it. Okay. So just the same trick that we played before. Right, and then you'll take, since it's a double pole, then you'll take the first derivative, right? You take the derivative of this and evaluate it at I to get the residue. Okay. So just using the theorem that we've used before. Okay. Okay. Right. So so what we have at this point, right, is the integral from here to here of f plus the integral over the upper semicircle. I mean, just the upper part of the half circle equals this thing, right? 2 pi over e cubed, right, for r. Right. Right, and what are we trying for? We want to take the limit of that as r goes to infinity, and we're hoping that this thing vanishes. Right? We're hoping that this thing vanishes, and if it does, then that will give us that our, so suffice it to show that the limit as r goes to infinity of CR of C dz is 0. Then the integral that we're interested in is going to be the real part of this, right? But the thing is real, so you just get 2 pi over e cubed. And if we were integrating the sign, then we see that we would get 0, right? Because we would get the imaginary part. Okay. Any questions on the method? Yeah, Michael.
Did we not want for phi of z, is it not z minus I squared?
Z minus I squared. No, because we want the residue at positive I, right? So we want e to the I 3z z plus I z minus I squared. We want to take the ones that don't involve we want this part, right? We want this to be a frequency.
Yeah.
Right. Right. So
my eye multiplication.
your eyeball what?
Well, I mean, it's the negative sign that's happening with the when they squared.
Sure. On Friday, I had an interesting sort of hallucinatory experience while I was eating dinner. Suddenly, the left part of my eye exploded with color in a sort of within a restricted boundary. So I was like, oh, boundary. So this sort of like boundary. There's sort of like a stained glass window appeared on the left side of my vision, with bright lights and I don't know. It was just the strangest thing. I was about to go to the hospital to have because it can be like my eye deteriorating. It could be so-called retinal detachment, which can instantly result in blindness. My father, when he was around my age, had something similar, and indeed lost his vision in one of his eyes this way. So I was going to go to the hospital, but it suddenly vanished. And the following day, when I went to the hospital, to the doctor to get it checked out, they said, "Oh, we don't know what it was." So anyway,
What were you eating?
dinner. Yeah, I was just eating dinner with my family, and suddenly it was like this. What's going on? Yeah, it was a stressful day, so maybe I don't know, maybe something strange happened to my brain. Anyway, so yeah, I thought you said something about your eyeball. Yeah, so just as a, those of you who have bad eyes, watch out for flashing lights, sudden streaks of darkness, or sudden, this sort of thing, something strange happening in your eye can lead to really almost like within a day you could go blind permanently.
And they can just fix it?
They cannot fix it.
No, but if you go and touch
If you go immediately, they'll laser your retina back onto your eye. They'll scar it. They will burn a scar that burns that part of your retina onto the eye to hold it there. Yeah. Which of course costs you some peripheral vision or some part of your vision, but not all of your vision. Yeah. Anyway, I wish somebody had told my dad. Okay. So what do we need to do, right? We only need to control that, right? So consider this thing, right? E to the I vz over c squared plus 1 squared dz cr, right? And we're hoping to make that thing small, right? And of course, the trick we'll play is the triangle inequality, right? So right? What kind of bounds are we going to get? Well, for the bottom part, we have very right. We know that, what do we know? C squared plus 1 is greater than or equal to, we're going to play the same trick that we always do, right? The reverse triangle inequality, right? So this is going to be bigger than r squared minus 1, right? So we divide by something smaller, right? So 1 over z squared plus 1 squared is going to be less than 1 over r squared minus 1 quantity squared. Right? So this is assuming r is bigger than 1, we're using the other half of triangle inequality. That gives us the bound on the denominator, right? And then for the numerator, it's easy, right? We know that this is smaller than e to the negative 3y, which is a positive number, and we can bound it by 1, okay? Because y is bigger than 0. So what you get altogether, right? So this thing is bounded by pi r over r squared minus 1 quantity squared, right? Which clearly goes to 0 as r goes to infinity. So that doesn't read. Okay. So a simple, not that fancy a trick, I'd say, right? You recognize your integral as the real part of an integral that you can evaluate as part of a contour integral. Right? Here's your integral, right? This in the limit is the integral of interest. This thing here, you can evaluate as a contour integral, as part of a contour integral. Okay. Any questions on that? Any questions? It's a simple idea, right? Just realize that your integral is the real part and the imaginary part is the little integral. Okay. So not that impressive. The next trick is a sort of more subtle one. Okay. So more subtle Fourier transform type integrals. So if we consider now the integral x sine x over x squared plus 40x. Okay. So this may look like it's the same sort of problem as before, right? But see what happens when you try to do the balance. It doesn't work, right? Because you have this, you're going to have r on the top, you're going to have r squared on the bottom. So basically you've got 1 over r, right? But that's no good, right? You need 1 over r to the p, where p is bigger than 1, right? We're going to, if you try to pull these bounds again, right, you would get r squared minus 4, and you get an r on the top, right? You get r over r squared minus 4, right? And then you get, so you get pi r squared over r squared minus 4, and as r goes to infinity, it doesn't go to 0, right? So this can't be approached in the same way. It can't be approached in such a simple way. But it is actually possible to get bounds on this. So and the authors actually go one direction, and at the very end of that, they give a reference. They say it's possible you could do this in a different way. Here's the different way. Okay, so you can, if you want, take a look at the author's approach, and at the very end of it, they say. There's an alternate approach using something called Jordan's Lemma, which you can find in a course of modern analysis by Whitaker and Watson, which is like from 1898. I actually used this book in my third year of college, a course in modern analysis. So it's still in print. It's that influential book, I think. So it's a pretty important book.
Is it still modern analysis though at that point?
Well, it's still the original thing. Yeah, it's not. It has like all these problems from the Tripos, say. It's from England, and it's more. It's sort of a historical. It's not modern analysis, but we're doing stuff that was done by Cauchy. So it's more modern than what we're doing actually. It's sort of a strange fact that most people's knowledge of mathematics, is like 17th century mathematics or most 18th century mathematics. You guys are heading, charging forward to the present, and in your theses probably have done something that actually involves something more modern. But there's a lot of one has to learn, one has to know a lot to get to the edge of modern mathematics.
It's probably more true in analysis than statistics or operations research.
Yeah, some more recent fields, I suppose. Yeah. Yeah. But there's always some sort of minimal amount of stuff that you need to learn. But it certainly is true that some fields require more preparation than others. For example, a lot of the RUs are combinatorics RUs. Oh, why is that? It's because you don't require that much. Some of the problems can be approached without that much machinery. But when I tried to do an RU, when I put in a proposal for an RU, there were sort of howls of concern about the amount of background that would be necessary to do it.
Did you get it?
No. Well, how should I say this? Yes and no. So the RU did go through. That is, with my project as one of the multiple proposals, the RU was funded, but I was never given the chance to run that RU. I was never given the chance to run my project. Yeah, such is life. Okay. Jordan's lemma. So this is not that deep a fact, but it's useful and kind of cool. Jordan's lemma. Let F be analytic outside of a circle of radius r naught. Let C naught, C sub r be as usual. Okay. Let M sub r denote an upper bound of the modulus of f on CR. Okay, so here it is. If the limit of M sub r as r goes to infinity is 0, then for every a bigger than 0, the limit as r goes to infinity of the integral of f of z e to the iaz dz is actually 0. And you see how that's going to be helpful to us, right? Our function is going to be z over z squared plus 4, for which we can find an upper bound on c sub r, right? Something like 1 over r. Right? And then, those bounds go to 0 as r goes to infinity. So this limit of the integral, the limit of the integral over the upper half circle goes to 0, and so that's what we wanted, right? We wanted to make that thing go to 0, but we couldn't do it by straightforward methods. However, we can do it by using Jordan's lemma. Okay. And then once we do that, we can play the same trick as before, right? The only thing that the only obstacle to us playing the same trick as before was that this piece over here wouldn't go to 0, but now it does. Now it will, using Jordan's theorem. Okay. Christian, do you have a question?
You got it.
Okay. Okay. So let me just complete the example first, and then I'll prove Jordan's theorem. Jordan's lemma. So completing the example. Okay, so just as before, let f of z be z e I z over c squared plus 4, right? It has simple poles at plus or minus 2i. The residue 1 over 2e squared at 2i, which is the only one we're interested in. So what that gives us is that 2 pi I times 1 over 2e squared, that's to say pi I over e squared, equals the limit as r goes to infinity of the integral of f over gamma sub r. Right? As before, which is the limit as r goes to infinity of the integral from r to r of f plus the integral of f over c sub r. Right. And then Jordan's lemma will tell us that this limit goes to 0, right? And this thing goes to the integral that we're interested in, right? So that, not exactly. It will go to the integral whose imaginary part is the integral we're interested in, right? So the imaginary part of the left-hand side equals the integral of interest, right? And so we get I over e squared is our answer. Yeah, Christian.
Does the condition for doing more general Fourier, or like the earlier, less subtle Fourier transform integrals, does that trick sort of decompose into this particular trick? So like, could you just do this trick every time?
So, I mean, this trick supersedes that trick.
Yeah.
Yeah.
Okay.
So, yeah. This trick. Yeah. Let me think about it to be completely certain, but I'm pretty sure that this trick basically does everything that the previous trick can do. It's just that, you know, it's not something you can do with your bare hands. You have to create the tool.
Yeah.
Yeah, the other one is just, you know, triangle inequality. Okay. So that is, you know, it's sort of overkill to invoke Jordan's lemma when you don't need to.
Mm-hmm.
Yeah. Okay. Other questions? Okay. So Jordan's lemma relies on something called Jordan's inequality. So relies on Jordan's inequality, which says this, that for all r greater than 0, the integral from 0 to pi of e to the minus r sine theta is less than pi over r. And the proof of the inequality is it goes like this. The first part is observe that if you look at the sine function, so here's theta, here's pi, and look at the sine function, here's pi over 2. Okay. And we're going to draw a line from here to here, right? This is the function y equals 2 theta over pi. So here is y equals sine theta. This line is y equals 2 theta over pi. Right. At pi over 2, you're going to reach a height of 1. Okay. Okay. So observe that for theta between 0 and pi over 2, sine theta is bigger than 2 theta over pi. Okay. So what does that give you? That gives you that e to the negative r sine theta is less than or equal to e to the negative r 2 theta over pi. Because this exponential function is increasing, right? And so the integral of the left guy is smaller than the integral of the right guy. Okay. When you evaluate the right guy, you get pi over 2r times 1 minus e to the minus r, which is less than pi over 2r. Okay. So what you get is that the first half of the integral that you're interested in, is less than half of the bound that you're interested in. Okay, and so the only thing left is to look at the other half of the integral. Okay, but the sine function is symmetric. The sine function is symmetric, and so when you evaluate the second half of the integral, you're going to get the same thing as the first half of the integral. Okay, and so you end up with the second half using symmetry. We see that the integral over the second half is also less than pi over 2. And so the two together give you the bound that you desire. So just a calculation. But the two together, this inequality gives you Jordan's lemma. So proof of Jordan's lemma. If we look at, we're trying to show that that this integral goes to 0. So let's look at the magnitude. And let's just evaluate it. So this is going to be the integral, right? The integral from 0 to pi of f of z e to the I a z I r e to the I theta d theta. That should z be r e to the I theta. dz is going to be I r e to the I theta d theta. Right. Right. And then we bound this using a triangle inequality. So move the absolute values inside, right? And we're going to get this is less than or equal to m r, the I vanishes, we get the integral from 0 to pi of e to the negative ay, right? So negative ay, y is r sine theta, right? And then d theta. Is everyone okay with that? Right? When we take the absolute value of the integrand, right? We take the absolute value of the integrand. We were given that f is bounded by m sub r. Right? M sub r was the bound for our f on c sub r. Right? So that's that. Right, the I, the size of I is just 1, the size of R is R, right? The size of e to the I theta is 1, right? So these guys, this becomes 1, this becomes 1, right? And then we have the magnitude of e I z, but as we said earlier, that's e to the negative ay, right? And our point is r cosine theta, r plus I r sine theta. Right? Our y is r sine theta, so that's this. Okay. So at this point, you see what we're going to do. We're going to use Jordan's inequality. Right? This thing here, m sub r, right? R is, so we're going to get pi over a r. Right, so we get m pi over a m sub r pi a. Sorry, I forgot to put in the bars. Right. And then as r goes to infinity, that goes to 0 by hypothesis.
When we use the fact that f is analytic outside of R naught,
Say it again?
the first stipulation of Jordan's lemma, you said f is analytic outside of the ball of radius R naught. What is R naught exactly?
It's just that you don't want to say that your function, the functions that you're interested in are going to have some finite singularities.
Okay.
Right? So what you want is you don't want to have a condition that your function be analytic on the whole upper half plane or something like that.
Yeah.
Right? So this is basically, I mean, if you want, you could say let this be analytic on the upper half plane, excluding the finite number of isolated singularities. That's basically to capture that possibility, which is what you're interested in. Yeah. So basically, I should say for all of these things, well, not for Jordan's inequality, but in the proof of Jordan's lemma, I should say that R should be greater than R naught, right? For this integral to make sense. For R bigger than R naught, then this is going to do. Questions? I should take a poll. I should poll again how people feel about this. Is it too easy? Is it too easy? Is it boring? I think it's boring. It could be sort of boring. I think it's cool. I think it's good. But you see that there are sort of specific. There are kind of there's a purpose to this sort of thing, to evaluate these integrals, right, that arise in Fourier analysis. Right? So there was a concern that this method answered. Now, will you ever be concerned with evaluating intervals that arise in Fourier transforms later? Maybe. I guess that'll depend on if I ever get to run the course that I was going to run in place of this course. Okay. Second to last trick, I think. Singularities on the real axis. But really, not any singularities. We're going to have a particular case. Suppose your function has simple poles on the real axis, right? And somebody says, "I'd like you to evaluate this improper integral." What they really mean by that is they're not asking you to evaluate the integral on the whole real line, but rather to do something like a principal value integral. So I'm just going to draw the case of a single singularity. Okay, so suppose you have at some t naught, there's a place where the function has a simple pole. Okay. What do you mean by the integral from negative infinity to positive infinity? What you really mean, or what would I mean if I'm saying the integral from a to b, where a is here and b is here? Okay. The way we're going to define that is basically like the principal value. We'll define that as the limit as r goes to 0 of the integral from a to t naught minus r plus the integral from t naught plus r to b of f of x dx. Okay, so we take a symmetric chunk out of the integral, and we let that thing tend to 0 in a symmetric way. Okay, and that's going to be the definition of this integral. Okay, and so when somebody wants the integral from negative infinity to positive infinity, what that's going to mean is that you'll take basically a finite. You have the integral from b to infinity. You have the integral from negative infinity to a. And suppose that there are a bunch of singularities here. At each one of those, you're going to play this game, right? You're going to have the integral from a to b, but it will be expressed as this sort of thing where you've taken out symmetric intervals around each thing and let them shrink in a symmetric manner. Okay, so that's what we mean. So this is basically principal value of an integral with singularities on the real line. I've talked it rather than written it, and I hope you know what I mean. Okay, so that's the sort of thing that we'll be interested in evaluating. For example, the integral of sine x over x from negative infinity to positive infinity. or maybe more sophisticated, sine x over x minus 1, x squared plus 4, x squared, yeah, that's good. So in any case, we'll be interested in evaluating things that have singularities on the boundary. Okay. And the main tool that we're going to use is a simple one. It's the following lemma. Basically, we're just going to do the same thing as before, but we need to modify to compensate for these simple poles. And what will allow the extent we need to modify will be made evident in this following lemma. So if f has a simple pole on the x-axis, simple pole t naught on the x-axis, then the limit as r goes to 0 of the integral over c sub little r is pi I times the residue of f at t naught, where c sub r is this tiny it's t naught plus r I theta, where theta goes between 0 and pi. Okay. So here's your t naught, and then you're going to take t naught plus r, right? So some small r, ei theta. So the radius of this is r. So you take these little guys, little upper semicircles centered at t naught, and those guys are the c sub r's. So if we take the integral of f over that guy as r goes to 0, what we're going to get is pi I times the residue at that point. So the proof of this is just a calculation. So well, look, f has a simple pole at t naught. So f of z equals v1 over z minus t naught plus g of z for some g analytic. You have a Laurent expansion. Right. This is the power series part. This is the principal part. And then you just evaluate. You say, well, look, the integral of f over c sub y is just b1 I r e theta d theta over r e I theta from 0 to pi. That's the integral of this first part, right? And then we have the integral of the second part, g of t naught plus r e I theta, I r e to the I theta d theta. Okay, so you just evaluate your contour integral. Your z is this, right? T naught plus r e I theta. And so what you get, of course these guys cancel. You get I, b, pi, I, plus the integral of g t naught plus bar I theta I r theta theta. So this will be 1. Okay, and then say let's show that this thing goes to 0 as r goes to 0. Okay. So right, if we show that, then we're done, right? Because what we'd get is that the limit as r goes to 0 of this is pi I times the residue, right? Plus 0. Right? And that's what we're hoping, that the limit of this integral as r goes to 0 is pi times the residue of t naught. Okay. So at this point, it suffices to show that that the limit as r goes to 0 of this thing is 0. Okay. Okay. But this is easy because G is analytic, right? So it's continuous at t naught. So if we try to bound the size of this thing, we know that this is bounded by some m for all smaller than some small r. Okay. Right. Right. You just you take some small neighborhood of t naught. And you have a continuous function on this closed neighborhood. You get some bound, right? Just by continuous function on a complex set, say. So you get some bound for that, and so this thing is less than or equal to m times r times pi, right? Which of course goes to 0 as r goes down to 0. Okay, so that gives it to you, right? The limit, as you take the integrals over these upper half circles, and you let the integral over that let the radius of those guys tend to 0. What you're going to pick up is pi I times the residue of the at that point. Okay. Right. And it's sort of funny, right? If we had integrated only over a quarter of the circle, we would have gotten pi over 2I times the residue. Right. So it's sort of like depending on okay, so it's sort of funny, right? It basically, the amount you go around the circle, you're going to pick up, a proportionate amount of the residue, right? As you go in. Okay. So what does this give us? How do we use this lemma to solve to evaluate these sorts of problems? I'll just sketch it out, and we'll start off with an example this next time. So what you do is like this, right? Somebody asks you to evaluate this sort of thing as a principal value integral. and you have some simple poles. You have some simple poles here, and you have some singularities above. And so what you do is you take, you take your R, and you create you create your gamma R. But down here, your gamma R is going to go like this. It's going to avoid each of these guys. So, say, you take your R big enough that one over R, you take, say, for example, you take the radii to be 1 over R, where R is chosen big enough that none of these guys overlap with each other. Okay. So what does that give you? That gives you that the integral of f over gamma sub r, right? Like this. I'm going to call each of these guys C sub rho 1, C sub rho 2, C sub rho 3, C sub rho 10. Okay, and I'm going to call these lines L1, L2, blah, 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 blah. So the residue theorem then is going to give you that the integral over the upper part, the integral over the upper part, plus the integral over each of these guys, right? So the integrals over the C sub rho I, plus the integrals over the line segments, right? All of that together is going to be 2 pi I times the sum of the residues. Right, for the residues, these guys here. Right? Okay. And then as r goes to infinity, what's going to happen? As r goes to infinity, what's going to happen is, if you're lucky, is that this thing is going to vanish, right? If under certain conditions, this thing is going to vanish. This thing is going to be your integral of interest, right? This is going to be your integral of interest. And what's this? This is going to be the sum of the. This is going to be pi I times the sum of the residues at these points. At z equals t sub I. Right? These guys on there, but in the wrong direction. So it's going to be minus, right? Because these are all going clockwise rather than counterclockwise. Okay. Right? So what's going to happen in the end? Right? Ultimately, under certain conditions, right, your integral is going to be pi I times the sum of the residues on the real line plus 2 pi I times the sum of the residues in the at point. And so that we'll do an example of that next time. Okay. And then we'll play the last trick, and then we'll do something else. Okay, that's it for today.